Soilcast – Boden, Umwelt, Klima.
In the first textbook episode, we found out that soils consist of organic matter, life, air, water, and weathered rocks. We soil scientists like to divide these weathered rocks, also called mineral component of soil, into different fractions of grain sizes. And we don't just do that for fun. There is a good reason behind these distinctions. The different grain sizes give the soil very specific properties and even influence the soil's water storage and fertility. In fact, the particle size distribution is so important that soil scientists gave it a distinct name: texture. A soil with mostly small grain sizes has a fine texture, while a soil with mostly large grain sizes has a coarse texture. But what do I mean with small and large? Let's dig into that a bit. Grains smaller than 2 millimeters are referred to as coarse grains or gravel. The mineral components smaller than 2 millimeters are called fine earth fraction, and we separate them into sand, silt, and clay fractions. Sand is what you find at a beach, and this particle size is clearly visible by eye. The next particle size fraction is silt, and it's much smaller. Silt particles have roughly the diameter of a thin human hair, and only the larger silt particles are barely detectable by naked eye. Now, soil societies don't all agree on where the size boundary between sand and silt is. Here, we are going to stick to the world reference base of soils, and there, silt-sized particles are 63 micrometers to 2 micrometers in diameter. Even smaller than silt-sized particles are clay particles, with a size smaller than 2 micrometers. Now, this size difference is a bit hard to imagine, so I will try a more visual example. Imagine a ball with 1 meter diameter, like these big gym balls. This now represents a sand grain. Compared to this sand grain, the size of a clay particle would be just a pinhead. Clay particles are so small that if you put them in your mouth, you won't hear a crunch when you bite. Theoretically. In reality, you rarely find pure clays with always crunches if you eat soil. Trust me, cannot recommend. There are more hygienic and comfortable methods to find out about the clay content of your soil that I will explain in a minute. Okay, now we know about the different size fractions, but how does that influence soil properties? Let's take again our pinhead comparison from before. Imagine a room filled with these 1 meter diameter gym balls. There would be a lot of space left between the gym balls, right? In the case of soil, we call this empty space pore space, which can either be filled with water or air. So, a soil that mostly consists of sand has very big pores. Now, instead of gym balls, we fill the room with tons of tiny pinheads representing the clay particles. What happens with the air-filled space now? Compared to the airspace that was there when the room was filled with gym balls, the diameter of the pore space between the pinheads has now become much smaller. In a clay-rich soil, the pores are much smaller in diameter compared to the pores in a sandy soil. However, this does not mean that the total volume of pore space needs to change. Sand-rich soils and clay-rich soils can have the same amount of pore space. The only thing that really changes is the diameter of the pores. Now, the different pore sizes of clay-rich and sand-rich soils has implications on water storage. Which soil do you think can hold water better? Sand-rich soils usually have a poor water holding capacity because they cannot hold water well against gravity. Maybe you remember from your holidays at the beach how easily water vanishes if you pour it on the sand. So, plants growing on a sand-rich soil need to be resistant to drought because there is little water stored in the soil beneath in case of absent rainfall. But at least their big pore space makes sand-rich soils well aerated, which means that there is enough oxygen present for roots and microorganisms who depend on oxygen for their metabolism. In clay-rich soils, water does not drain easily, and these soils can store a lot of it because the pores are small and convoluted. In fact, the water is held so tightly in clay-rich soils that up to 35% of the volumetric water content in clay-rich soils is inaccessible to plants, because their suction force is simply not strong enough to extract the water stored in the tiny pores. So, clay-rich soils are also a challenging plant habitat. Now we have learned how particle size distribution can influence the water household of a soil. But even more soil properties are influenced by particle size distribution. Smaller soil particles have a large specific surface area, which means that they have a lot of area compared to their mass. If we were to compare the surface area of pure sand with a grain size of 2 millimeters and clay with a grain size of 2 micrometers, the specific surface area of the clay material would be more than 1,000 times larger. While the mid-size grain fraction silt has 1 square meter per gram of soil, in clay you would find up to 500 square meters per gram of clay. This means that in 1 gram of pure clay you find as much area as on a basketball court. In 1 gram of clay! Okay, this is cool, but why is it important? A lot can happen on the surface of a particle. These surfaces offer a lot of space for chemical reactions, plant nutrients, microorganisms, and pollutants. Sandy soils have much less specific surface area, which means that they cannot store as many plant nutrients as soils with a clay texture. Another property of clay-rich soils is that they are quite sticky and easily deformed, which makes them prone to soil compaction under wet conditions. However, not every clay-rich soil behaves the same way, since its properties mostly depend on which clay minerals are present. More on this in the following clay textbook episode. Now we have heard a lot about sand and clay, but totally forgot to mention the silt size fraction, which is in between both. What are the properties of a silt-rich soil? As you can imagine, they are a bit in between the two extremes of sand and clay-rich soils. Silt-rich soils have a medium to high ability to store plant nutrients. They have a medium water holding capacity and don't drain as quickly as sand, but also do not drain as slowly as clay soils. However, what makes them really stand out is their susceptibility to erosion. Since silt-sized particles are not as sticky as clay particles, but are also lighter than sand particles, water and wind can transport them easily and quickly. Especially wind can transport silt for hundreds of kilometers. In the United States, Argentina, Western Africa, Eastern Europe, and China are vast plains filled with mostly wind-transported silt. Once silt is transported by wind and deposits, it gets a new name: loess. On less material, new soils can form. These aeolian deposits of silt reach 300 to 400 meters deep in eastern China. Soils that formed on less material are very fertile. Their pores are big enough to make water accessible to plants, but also small enough to retain water against gravity. This also means that these soils are well aerated, which is important for microorganisms and plant roots. Soils that formed on less material have a well-suited specific surface area because they can store plant nutrients and also release more of them by chemical weathering. However, due to their susceptibility to erosion, they are challenging to work with in agriculture. We will talk more about soil erosion in a later textbook episode. Now we have talked about sandy, silty, and clayey soils. But how do we call a soil with a texture that consists of a mix of the three particle size fractions? We would call this a loam, and it's the most common soil texture to find. Loamy soils really have the best of the three worlds. They don't drain so quickly and can store a decent amount of water. Also, they can store exchange ions, meaning plant nutrients and pollutants, on their surfaces. And contrary to silty soil, they are not so prone to erosion because the clay content makes the soil stick together better. Now I'm sure you can't wait to find out what texture the soil in your garden has. Good thing you don't necessarily need a soil science laboratory to find out. You can just take a handful of soil and spray some water over it. Then try to roll it into a ball. If it does fall apart when you poke it, you have a sandy soil. If you can form it into a ribbon, the sand content is not very important. If you manage to make a ribbon longer than 5 centimeters, we come into the realm of high clay content. Just like in pottery, clay makes material plastic and moldable. Now, if you rub a part of the soil close to your ear and you hear a gritty sound, there might still be a considerable amount of sand in it. Pure silt feels a bit like flour. With a bit of experience, you will be able to tell the texture of a soil quite well in the field. If you want to do this step by step, I put a link to a proper guide in the show notes. Now we have talked a lot about sandy soils and clay soils. This was about the texture of soil, meaning the particle size distribution, and should not be confused with soil type. Texture is a very broad term, whereas the soil type tells you much more about the soil's properties. The soil type tells you a lot about how the soil formed and which characteristics it inherited from its parent material. The term parent material is what soil scientists call bedrock or the sediment on which soils form. I really like the term parent material because it basically makes the soil the child of the rock. So how do we find out which soil type lies beneath our feet? On the top, there are often fallen leaves and sticks, at least if you are in a forest. This dead plant material we call litter. The best way to find out on which soil type you're standing on is to create a soil profile. This is actually nothing more than a pit, which should be 2 by 1 meter in size and at least 1 meter deep. You should dig this soil profile deep enough to reach the parent material. Standing in a soil pit really is an amazing experience. You can see where the roots grew through the soil, maybe even spot an earthworm. If it is a waterlogged soil type, you might find yourself standing hips deep in water with a frog that keeps you company. To identify the correct soil type, the walls of the pit need to be scraped smoothly. You can then see very clearly that the soil is not homogeneous, but that it is divided into different, more or less horizontal sections. This looks as if the soil has different levels that lie on top of each other and might look like geological layers. However, do not call these horizontal planes layers, but horizons, because they do not form in the same manner as geological layers. While in geological layers, the oldest part is on the bottom because more and more material sediments on top. In a soil, it is the other way around. The oldest part of the soil is the surface, which has been exposed to weathering the longest, while the youngest part of the soil is at the interface to the parent material, deep below. So yeah, if you want to upset a soil scientist, you can talk about layers instead of horizons when you look at a soil profile. If you want to get an impression of different horizons, you can look at the Soilcast episode image. Here, a soil type called Luvisol is shown schematically, with its characteristic horizons which differ in colors very clearly from each other. Although these horizons look very different, they all originated from the same parent material. They developed in the course of soil formation as a product of different physico-chemical processes. One example would be clay displacement, in which the clay particles migrate from the whitish and low pH horizon of the Soilcast episode image downwards to the brown horizon with higher pH where the clay particles are deposited again. The amount of clay therefore decreases in the upper horizon and increases in the lower one. Just as an example of how these horizon colors come to be. We now know what soil horizons are and can understand soil types. Soil types give a name to the occurrence and sequence of horizons. For example, if I tell a fellow soil scientist that the Soilcast logo has a Luvisol in the background, they will immediately know how it looks like. In soil science, horizons are characterized by a fixed combination of different letters and numbers. This is rather complicated for untrained people, but it helps us soil scientists to understand the horizon sequence of a soil type without paraphrasing it. Countries and regions have different approaches to describe their soils. In Germany, soil scientists use the Ka6, which covers all soil types you find in Central Europe. The American classification, on the other hand, covers much more soil types that are found throughout the United States. To cover all soil types present around the world, I suggest you use the World Reference Base of Soil Resources, short WRB. The WRB does not only have different horizon designations in some cases, but also classifies soils differently. Since our English textbook episode should be accessible internationally, I will use the WRB. To illustrate the difference between soil type and texture again, I would like to give a few examples here. You still remember the löss I talked about a few minutes ago. Silt has been transported by wind. Once it deposits, soil formation can start on the löss material. Different soil types can develop out of this löss parent material. For example, the Lubisol in the background of the Soilcast logo formed from löss material in the temperate, moist climate like Germany. However, if the climate is more continental with less rain and therefore less chemical weathering, Chernozems form from löss material. Chernozems don't have these colorful horizons like Lubisols, but they are black in the upper horizons because they store so much carbon. You can find these very fertile soils in parts of Eastern Europe, especially in the Ukraine. So even though Lubisol and Chernozem both have the same texture, they are assigned different soil types because they differ in many properties. Although you get dirty quite often in soil science, and let's be honest, we soil scientists like to be in touch with our subject, we nevertheless like to leave our study sites tidily. To ensure that no one falls into the pit later and that no animals die there, we should fill our soil pit again as soon as all the necessary soil samples have been taken. And because we now know about the different horizons and don't want to destroy the soil, we don't just pour the excavated material into the pit, but in the exact order in which we took it out. In this episode, we dug quite deeply into the topic of soil texture and soil types. I hope that you now know the difference between the two and that your mental soil pit is filled with new soil science knowledge. We will let it rest until the next episode. See you there!
Der Soilcast ist für euch kostenlos und das soll auch so bleiben. Ihr könnt uns dabei helfen. Derzeit unterstützen uns etwa 1% unserer Zuhörerinnen und Zuhörer, zum Beispiel durch eine kleine Überweisung auf das Geschäftskonto oder via PayPal. Wie das genau funktioniert, seht ihr auf soilcast.de unter dem Punkt Unterstützen. Das Geld wird für die digitale Infrastruktur verwendet und darüber hinaus in Technik investiert. Vielen Dank für eure Unterstützung.